Yeah.
It's time. We have an absolutely wonderful, exciting colloquium for you today. Arguably one of the major unsolved problems in astronomy and astrophysics. And we have none other than Professor Bastian, Nate Bastian from Liverpool John Moores University, otherwise known as LJMU, to talk to us about it today. He's a professor of astrophysics. He's a member of the Royal Society of University Research Fellows, and he's the director of research at the Astrophysics Research Institute at LJMU. He does have his roots in the United States. I must confess, and he will confess, that he got his undergraduate degree from University of Wisconsin at Madison. He got his PhD from the University of Utrecht under the direction of Professor Henny Lammers, who many of us have known for a long time. And he also has a secret habit, which is climbing mountains. And if you look at his website, you'll find that all of the workshops that he has organized are always at the base of a mountain. So you can guess what they do during their coffee breaks and after dinner and before breakfast and things like that. He's worked on stellar clusters, star formation, and stellar populations. And he has an amazing talent for explaining things exceedingly well and making complex ideas very understandable. He's written 2 major reviews in the annual reviews of astronomy and astrophysics, which are highly cited. As a matter of fact, I discovered they're the most cited by factors of 2 over all the other articles that have appeared in that journal of that volume of that year. Yes. So, without further ado, I introduce you to Nate Bastian, Professor Bastian.
Thank you very much for that wonderful introduction, which I can live up to the test. I've turned it on? All right. Is it on? Yeah? Okay, great. So I want to tell you a bit about a problem, the origin of multiple populations within stellar clusters, and I'll explain, of course, what they are. But I'm going to give the game away a little bit, and unfortunately, it's going to be a bit of a demotivational talk, because the answer is we have no idea what's causing this. And I'll go through some of the models that have been put forward, including my own, and why they don't work. And so hopefully it motivates someone to get interested in the topic, and I think we really need some new ideas, but don't expect an answer at the end of this. This was work that actually Selma Demink, your new faculty member here, was the original one to get me interested in this. And also lots of the work that I'll be presenting today was done by Ivan Cabrera-Ziri, who's now a Hubble Fellow here at CFA. So when you go out in the night sky and you observe your favorite galaxy, you end up with all these little points of light that get in the way when you're trying to study the galaxy itself. And if you had infinite resolution, and you could zoom in with the Hubble Space Telescope like we can in the Milky Way, what you'd see is that almost all of the points of light within this image are in fact not individual stars or background galaxies, but they are globular clusters. These are balls, dense balls of gravitationally bound stars that are typically old. Now, again, if you had infinite resolution and you could go out and make a CMD of your favorite cluster, again, what you see is that they're predominantly old, about 10 gig years or so. They're not uniform in age, but they're all, say, generally 10 gig years or more, and by and large, they're metal poor. Again, there's a wide range of metallicities, but at least compared to things that are forming today, solar metallicity, they're all metal poor. And because of this, we know that they're some of the oldest luminous objects in the universe, and we see that the properties are actually varying as a function of their host galaxy. And so they've had a long promise that they maybe could be used as tracers for the formation and evolution of galaxies. And so, of course, there's a long history of using globular clusters. They've been used to determine, of course, the structure of the Milky Way, the famous debates, the 1910s. They've been used to understand and calibrate stellar evolution and stellar populations. The kind of first reference I could see of a really basic color magnitude diagram is in Eddington's book, 1926. They've been used to constrain the formation and evolution of the Milky Way, as well as people have been trying to step out and go to extra nearby galaxies. And of course, they've been used to try to study stellar exotica, like low-mass X-ray binaries, types of stars, type of stellar phenomenon that you just don't see very often in the field. Due to their high densities, stars interact much more than they do in the field, so you end up with some crazy things that you wouldn't get from single-star evolution. And so if you go back to your Astronomy 101 course, what we're taught is that there's two types of stellar clusters, right? There's open clusters, which are low mass, low density systems that by and large live in the disk of the Milky Way. And because they're young, and they're typically young, they are solar metallicity about. And you can contrast that with globular clusters. They live in the bulge and halo of the Milky Way. These are high mass, high density systems, tens of thousands, up to millions of members. They're all old, and because they're old, they're low metallicity. And one of the things that we've learned in the past, say, 2 decades is that this dichotomy of breaking things up into open clusters and globular clusters isn't real. It is simply due to a selection effect of living in the disk of a spiral galaxy. So we have a very biased view of what we can see. But one of the things that clusters have in common is that they're historically viewed as simple stellar populations. What that means that all stars within them have the same age and the same abundances, right? And because of that, then you can use them to calibrate stellar models. They have a range of stellar masses and possibly rotation rates. Okay, and so yeah, there's a lot of work, and every time a new isochrones or new stellar models come out, they have to calibrate against large samples of these open or globular clusters, because that is what a basic still a simple stellar population is supposed to be. And it's also been kind of gospel for the past, 100 years, that globular clusters must be unique. They must be special. So they must only form, because they're all old, in the special conditions of the early universe. But the last 2 decades have shown that, in fact, despite them appearing as very simple systems, in fact, there's a bunch of surprises hidden within them as soon as you start looking in a little bit of detail. So if we go back to our favorite cluster here, so this is NGC 2808. This is a Milky Way globular cluster. And when you observe its CMD, you see it's just normal. You got a main sequence turnoff, red giant branch. There's nothing really special about that at all. But if you go out and observe it with a Hubble Space Telescope, the advanced camera for surveys was really the first one to really nail this down. And you zoom in on just the main sequence here, is you see, in fact, it's not a simple stellar population at all. In fact, it's made up of 3 or more parallel sequences that can only, in this particular case, can only be reproduced, not by different ages, not by different metal contents, but by different helium values. And so if the nominal main sequence is y, typical cosmological value of y of 0.25 or so, the most extreme one must be y of 0.4 in terms of mass fraction. So there's a huge variation of helium amongst their populations on the main sequence. So it's not a stellar evolutionary effect. These stars must have been born with this, because they wouldn't be able to produce on the main sequence this type of helium spread. But there's been other surprises as well. So this is an image of Omega Cen. This is the most massive globular cluster in the Milky Way. It's a few million solar masses. It's about 12 gigayears old. And if you go out and you observe your favorite galaxy merger, in this case, this is the Antennae galaxy. This is 2 spiral galaxies that are merging today. You can see they're undergoing a starburst. And if with HST, you could actually go out and zoom in on individual sources. This is one. This is called Knot S. This is a very young cluster, about 7 million years, based on UV spectroscopy or optical spectroscopy. You can tell it's very young, but it's got the same mass. It's a few million solar masses, and in fact, its half-light radius is about half that of Omega Cen. So it's significantly denser than the most massive cluster in the Milky Way. And so based on this, we can say, they have similar masses, they have similar sizes, that in fact, globular clusters are still forming in the local universe today. Now, what does that mean? It means that at least we find objects that would look exactly what we expect Omega Cen looked like, maybe not that particular example, but an average globular cluster looked like when it was forming at high redshift. And so throughout the talk, I'll be using objects like this to understand how objects like that formed and evolved. All right, so so that was the Antennae galaxies. It's not unique. We actually see this across star-forming galaxies today. These are 2 galaxy mergers. You can tell that. These are spiral galaxies. You can see the nice tidal tails coming off here. And again, if you zoom in with HST, you see that, in fact, they are forming these extremely massive clusters within them. The most massive one to date, as I mentioned earlier today, is W3 in this galaxy, which is 10 to the 8 solar masses. But it's a stellar cluster. It's 15 parsecs in radius. And if you think that one's an odd one out, the next most massive one in the cluster is 10 to the 7. The next one after that is 9 times 10 to the 6. And you have a full mass function all the way down. So you can any mass that you want, they're forming within this galaxy. And the one over here, this is one Ivan has studied in a lot of detail. And this is a 100 million year old cluster, and it's 10 to the 7 solar masses. So if you take, say, a mass cut at 10 to the 7, we can find a system that formed virtually at any age, all the way from forming today, a few million years old, all the way up to ancient globular clusters in the Milky Way, or M31. But they're not just in galaxy mergers. It's anywhere where the star formation rate is vigorous enough. And so this is another one, NGC 1705, a nearby dwarf starburst galaxy that's formed a million solar mass cluster about 15 million years ago. And this is close enough that we could actually resolve it into its individual stars. So you can really get a CMD-based age for this. So jumping back to the ancient globular clusters, that they're not simple stellar populations, when it's now gone out and you observe clusters again with WIPIC 3, and you can go into with HST, and you can go into the ultraviolet, what you see is that none of the clusters are in fact simple stellar populations. None of them have a single main sequence or a single red giant branch. You always see these kind of spreads on the red giant branch and the main sequence. And if you then go to chemical space, so you go on out and you measure abundances of individual stars within the cluster, you see that they're not uniform at all. And so these are each point here, you can ignore the colors, but each point here is a star in 47 Tuc, which is a massive Milky Way cluster. And we can see is that there's a clear spread in oxygen and sodium, and in fact there's this anti-correlation. And so every cluster that's been studied in necessary details show these types of chemical abundance spreads within them. However, they're all different in the details. Every cluster looks unique. So while there's overall trends in the abundance space, every cluster has this unique fingerprint in abundance space that you can actually use to identify it. All right, so coming back to and just using 2808 as a test case, so this is the one with crazy helium spreads, at least in stars on the main sequence. We see that in this case, 60% of the stars are enriched. These are going to be enriched or second population or anomalous or strange stars. And 40% of the stars are normal. And by normal, meaning that these are the types of stars you might find in the field at that given metallicity. And again, in this particular case, it's not age or metallicity differences. It's only helium differences that can explain it. But this is a relatively extreme case. But again, every cluster shows this. So every cluster study today does have a helium spread. They all have abundance spreads in sodium, nitrogen, CNO cycle, all that kind of stuff. And so what are the spreads caused by when you look at CMDs? Well, if you look in ultraviolet colors, really what you're seeing are spreads between stars in the same cluster in CNO. In particular, nitrogen is the main one. If instead you look in the optical, you see spreads in helium. Again, I get the question always after I give the seminar, are you sure there's not age spreads? There may be age spreads, although I'll come to that at the end, but age spreads or iron spreads are not driving these CMDs. And so in fact, you can do this, and if you look at the ancient globular clusters, the best constraint you can do is that you know that age is not driving these differences, and say, is there an age spread? Delta age is going to be less than about 200 to 300 million years within the ancient globular clusters. It's an upper limit. You really can't do better in these kind of ancient stellar populations. Okay. So, trying to put this in context, just to drive home just how weird globular clusters actually are, you can put it another way. You say stars, and at least stars and globular clusters, know where they form. And what do I mean by that? So if you come to our favorite diagram, sodium, oxygen, and again, so these are going to be the primordial or population 1, and then our stars up here are going to be the enriched or second population stars. You can compare them in numbers. So if you go to the field and you made this exact same plot for field stars, 97% of halo stars, at least at lower metallicities, are going to be in this region down here, where that only makes up 40% of cluster stars at that metallicity. 3% of halo stars are going to be up in that region, where 60% or more of globular cluster stars are going to be up in that region. So globular clusters really are anomalous. The average star in a globular cluster looks nothing like the average star in the field. And in fact, you could say 3% of halo stars look like that. Almost certainly those are coming from disrupted globular clusters. In fact, they're all coming from globular clusters. So what's the observable? So we have some main anti-correlations that people make a big deal about: sodium and oxygen, nitrogen and carbon. We see large spreads in aluminum. We have small or no spreads in magnesium for most clusters. There's some spread in other light elements, say CNO, and little or no spread in iron, at least for the vast majority of clusters. We see discrete or spread main sequence turnoffs. Basically, every evolutionary phase, you see things that are not well described by a simple stellar population. This is not a metallicity effect. It's very important that you find this in the most metal poor clusters. So you could say, okay, -2.5 or so, but they're also found in globular clusters with solar metallicity. There's 2 clusters in the bulge have been studied that are near solar metallicity, and they have the exact same trends that you see across. So it's not, you can't invoke any metallicity dependent source to do this. And so what could do it? So all the elements that I mentioned here, these are all elements that are touched by hot hydrogen burning. So almost all the ideas that people have been put forward is you're going to use hot stars that are burning hot hydrogen, so either massive stars or AGB stars, in order to basically process material, and then you're going to put that material into future generations of stars. And one thing, the first thing I look into once Selma told me about this is that surely it's supernovae. Surely I could find some sort of crazy supernova, some POP3 type thing that's causing this, but it turns out that a supernova actually give all the wrong elements as well, including iron. You should expect iron spreads. And so you get all the wrong trends, and so yeah, so supernova can't do it. All right, so one of at least the main ideas that have been put forward in this are AGB stars, so evolved 3 to 8 solar mass stars. Although, just a little detail is they actually give a sodium-oxygen correlation instead of anti-correlation. Rapidly rotating high mass stars have they do this. Interactive massive binaries is what we invoked in our model. Do this, or extremely massive stars. And this is a new idea that has been put forward. And just to show you how out of ideas the community is, these stars are obviously hypothesized to be about 10,000 solar masses. And so that's what we're left with these days. All right. So just to give you a brief taste of the kind of models that have been put forward, I'll talk about the AGB models. I'll kind of poke some holes into it, but the same basic flaws or the same basic concepts apply to all the other models, or most of the other models anyway. So the basic idea is you have multiple epochs of star formation within an individual cluster. Okay? And so you have the ejecta of a first generation of stars, say your AGB stars, or a first generation that evolved. They process the material, they undergo hot hydrogen burning, they have winds or something that blows off that material. It mixes with primordial material, so you need that to be left over from the formation of the first generation, and then you form a second generation. All right? And I say not all stars can do this, so you either adopt AGB stars, and therefore your time scales are going to be tens or hundreds of mega years, or you can adopt massive stars, then your time scales are going to be just a few mega years. But just to say overall, while this is very conceptually simple, they're extremely ad hoc. And so they had a lot of different knobs and adjustable parameters that they can mix. There's a strange mix of theory and fixes to fit the observation. So it took me a few months anyway to really dig through the literature and understand what was observed versus what was implied. And overall, they assume that a cluster can hold on to gas expelled from stars and accrete gas for tens to hundreds of mega years. And from somebody I come from the kind of the young massive cluster regime, as that was a surprising assumption to make because we haven't seen that. But I'll come to that now. So this is just a little cartoon version of the AGB scenario. So you form your first generation of stars here. After 30 million years, the first AGB stars evolve and they start puffing off their winds. And so you collect, and then those winds are allowed to cool and fall into the center of the cluster. You then accrete gas, in fact, a lot of gas in order to mix with that material there. You form a second generation of stars in the center of the cluster, but even then you don't get the right answer. You have to then assume and invoke that clusters then lose 90% of their first generation of stars in order to get the number ratios right and to solve the so-called mass budget problem. Basically, to have enough material here, you need the stars, but then you don't see them today, so you have to get rid of them. So in fact, in the AGB models, 95% of these first generation stars must then be lost, and how they're lost is not actually defined within the models. They just assume that they can go out, where dynamicists say that's not really possible. Okay, so what are the predictions of this kind of scenario? So the first prediction is that the second generation or the second population will be more centrally concentrated. So it should be more focused towards the center of the cluster. And that's actually probably true. Most clusters show that, although there are some complications. Not all clusters show that, but by and large, at least to first order, that was a prediction that was confirmed. The second is that in order to have enough material to form the second generation, globular clusters must have been 10 to 100 times more massive than presently seen. This is a so-called mass budget problem. And you can actually test that directly by going to dwarf galaxies and counting up the number of stars that you see in a certain metallicity bin in globular clusters, count the same number of stars in the field, and say how many stars, you need 100 times more, at least, if not more. And in fact, it doesn't work. So there's only about a factor of 4. So right away, that's directly contradicted by observations of dwarfs. And this was a work done a lot by Soren Larsen. It's assumed that clusters can retain ejecta and accreted gas for long periods. And then, if this is true, all these models are doing, they're not invoking anything new about globular clusters or high redshift universe. All they're using is the gravitational potential of the cluster. So the same thing should be happening in young massive clusters today, even if they're totally different objects. It's just the gravitational potential that's being used. So we should see that clusters should show an age spread, these massive clusters that we're observing today, or ongoing star formation where we can see the second generation forming. So we can actually go out and test this now. So this is something I did with Ivan, where we went to the antennae galaxies. This is this galaxy merger. It's got a ton of very massive clusters, say 10 to the 6, a million solar masses and above. We got spectra of each one of these, right? All the stars shown here. These are just some of the images with the slits overdone. And what we should expect to see then is we should expect to see an integrated spectrum, which is going to look like an A star, essentially. And on top of that, we should see superimposed emission lines. The emission lines are going to be coming from the new generation of stars that are forming today, right? So it's just simply, do you see ongoing star formation with any of these clusters? And that's shown here, and so you can see, if you look at H beta, you can see you don't see that at all, well, except for that case. And I'm embarrassed to say that I published this in 2009, and I never even noticed that guy. This would have been the smoking gun, and this would have really driven home that you can't have multiple generations of stars within clusters. And in fact, it took another team to discover this, and they were writing a Nature paper to show this is the smoking gun. And to their credit, they never submitted it because they recognized and said, well, it turns out if you really zoom in here, you can see that the lines are offset. There's actually a different velocity. And so if you look here, it's this guy right here. If you squint, you can see there's a red thing here. It's just an H2 region that happens to be next to the cluster. It's totally unassociated. It's something like 50 kilometers per second offset. And so what's the odds of that? Well, it turns out quite high. This is an interacting galaxy. There's just H alpha everywhere. And so it had nothing to do with the cluster. And so in fact now, so this was not one. This was one that there was no evidence of ongoing star formation within the cluster. So that was just the first 9. We did this for 140 other clusters that were taken from the literature. And this is their age and mass. So age is on the x-axis. Mass of the clusters is here. To guide your eye, an average typical globular cluster in the Milky Way is shown as the blue line in terms of mass. They're all old. And we looked at clusters between 10 million years and a gig year. This is the range where we thought we'd have a second generation forming. And what you find is that none of the clusters that were found, that were studied, had any evidence of ongoing star formation within them. Some of them, the different symbols here, these are clusters you can resolve. You can actually look for O stars, and there was none found. And so basically, with these rule out that there'd be continuous formation within them, or at least continuous formation where you form high mass stars in the second generation, and you can actually just favor discrete bursts. Ivan, for his thesis, looked at this a bit deeper. He went to some of these, and he looked at doing the using the integrated spectroscopy and do the star formation history, just like the galaxy people do. And you can see it was consistent with a simple stellar population. You didn't see multiple epochs of star formation going on. Then he went with ALMA, and he picked some of these clusters here, and went really deep to see is there any evidence of gas or dust within these clusters. And again, the answer was no. And you could tell all that, but the optical extinction was also near 0. So it seems that clusters are gas-free, and they don't show evidence of second or multiple generations of stars within them. So just to summarize what we can take away from these young clusters, they're actually gas-free at very young ages. I didn't present that, but we have evidence that 3 million years or less, and therefore that actually rules out this kind of massive star scenario. There's no evidence of ongoing star formation in any of the young massive clusters studied to date, and then we can get that also from integrated spectroscopy. We don't see extended star formation histories. We don't find gas or dust within any of the clusters that have been studied to date. And therefore, models of multiple star-forming events are just favored by observations of young massive clusters. And therefore, previous models don't agree with observations. And this was usually the part of the talk that I would then switch over to my model of shows how well we can do. And that model was put forward after we had all of these constraints. So therefore, it satisfies all of these constraints. But I'm not even going to waste your time today presenting that model. And I'll show you at the end why, is that it falls foul of a whole list of other constraints that have been put forward. So it's equally wrong as all the rest. So we're kind of stuck. We don't have a model really to go test. But one of the questions that I guess a lot of people here are thinking of, I'm talking about young massive clusters like they're the same thing as globular clusters, right? So you ask the question, do you see the chemical spreads in these young massive clusters? So we went out to test that. And you can do that because we get a little bit lucky. That we have a neighbor, the Large and Small Magellanic Clouds, and they've been forming clusters more or less continuously for the past 12 gig years. So you can find relatively massive clusters, 10 to the 5 solar masses and above, so globular cluster-like masses, at virtually any age. And they're close enough that you can get stars, get individual spectroscopy of stars within all the clusters, but we also can get photometry. And so we've been going out and we did an HST study over the past few cycles to study a whole bunch of clusters at different ages to see if we see evidence for chemical spreads, multiple populations. And on top of that, we also have a VLT survey to look for basically nitrogen variations spectroscopically. So how does this work? So this is an example. This is red giant branch spectra, model spectra. And you can see here is that there is a nitrogen molecular line right here. And then on the bottom here is you see the difference between the two spectra is shown as black, and you see HST filters are shown as well. And so we picked this filter right here, this F343N filter, that's centered right on this nitrogen line so that we can see basically if there's nitrogen variations within a cluster. And it turns out to be extremely sensitive. And then we also tested this, of course, with directly nitrogen abundances measured spectroscopically. So this is our sample. The yellow shows the initial sample. The blue shows the extension that we got last year. And so you can see is that overall our clusters are quite massive. Again, globular clusters are kind of this mass. There's some lower mass, but overall we go from about 1 gig year or so all the way up to 10 gig years or so. And so we can actually look for multiple populations within them. All right. So just to say, we included this cluster up here. This is NGC 121 in the Small Magellanic Clouds. And why did we include it? Well, it's old. It's a classic globular cluster in every sense. If we didn't find multiple populations there, then we don't know what we're doing, right? So no one would believe any of the rest of the work. So we picked a cluster that had to be there, and in fact, we found multiple populations. And I'll show you exactly what I meant. And so the next thing, and then I'll kind of take you through how the data came in. And so try to build up some excitement within this, because the same we had to go through this emotional roller coaster as well. And then the next clusters that came in were these intermediate age ones. And so are these globular clusters? It depends which paper you read. Some call them globular clusters, some call them open clusters. You know, it's an arbitrary definition. And so this is Lindsay 1. It's the first one that came in. It's about 7.5 gig years. It's a few times 10 to the 5 solar masses. Its formation redshift, try to put it in cosmological terms, is redshift of 1. So it's definitively non-cosmological. It's not early universe. It's local universe for many people. And if you use our filter combination, so this is a super color, so it's a difference between two colors, which is really good at picking up the presence of multiple populations, versus magnitude. You can see it here, so this is the individual stars, and this is the HISS diagram. You can see, in fact, we see a split RGB there. If you take a cut across in this direction here, kind of perpendicular, and you make a histogram, you end up with the center diagram right there. And so you can see it's clearly bimodal. And so then we went out and you get spectra of stars in each one of those, and you can plot the nitrogen versus carbon. You can see there's a very clear nitrogen spread of about 1.5 dex. And so this is a case, it's very clear that there's multiple populations within this cluster. So skip to the end. What do you get from all this? So again, this is the region of parameter space. These are ancient globular clusters, the classic globular clusters. They all have multiple population state. Open clusters I didn't talk about, but people then have gone search for open clusters of the Milky Way. They're going to be down in this region down here. None have found been multiple populations so far. What did we find? First, all of these clusters were multiple populations. So we saw this, we were super excited. So what that meant was, of course, we're going to find multiple populations everywhere, right? This is just going to be a generic effect of young massive clusters, or massive cluster formation, something to do with that. So the next one that came in, sorry, skipped ahead, is going to be one of these guys. I can't remember which one. NGC 419. So this is a cluster in the SMC, 1.5 gig years old, 2 times 10 to the 5. And then this is, again, some supercolor CMD. These are the data points. This is the kind of spread we are expecting. And there's no spread. In fact, it's basically consistent with at least a very small spread or no spread whatsoever. So there's no spread there. And that was confusing and very disappointing, but it's what you get. All right, so no multiple populations there. And so if we skip through, none of those were found with multiple populations. So that was a bit surprising. So you can put other clusters on this. So then, oh yeah, I don't have time to go into the details, but Ivan and Carmela Lardo went out and they came up with a really clever technique to find multiple populations in integrated spectroscopy, where they could go for much younger clusters, 30, 40 million years, but then much more massive, and they didn't find evidence for multiple populations in any of them. So it's a different technique, but it's complementary to what we've been presenting here. This is Berkeley 39. This is the most massive open cluster that has been searched to date. That doesn't show it as well. And then we came with this cluster, 1978. And this is going to be the kind of Rosetta Stone cluster for future studies. And that does show it. It shows very clearly, both spectroscopically and photometrically, we see multiple populations within that. And then we could overput the new clusters within this, and you can see is that we have another cluster down here that doesn't show it, but all of these clusters do. And so you can see something happens. All of a sudden, multiple populations appear, but there also has to be some very important mass effect, cluster mass effect as well. And then just to say, recently, again, with integrated light techniques, we found that we had a cluster 10 to the 7 solar masses or so at about 3 or 4 gig years, and that does show it very clearly as well. So again, all clusters that have been observed, at least above some mass threshold, above 2 gig years show it. All the ones below do not. And so this puts it into context a little bit. So again, age on the x-axis. The y-axis is a proxy for nitrogen spreads. It's basically the width of the RGB and our special combination of filters. And you can see, and then we went out and we got a bunch of Milky Way globular clusters as well. And you can see is that there's a very clear correlation. Not only is there a step function at 2 gig years, is that there's a clear correlation with age as well. And so for the ones where multiple populations were not detected are just shown as upper limits. And you could say that, well, these guys are also, we know there's a mass dependence. We see that in Milky Way globular clusters. So you should remove them because these guys are not of the same mass range, about a factor of 10 higher. But even without those, you clearly see a trend with age. And this is one of the unsolved. We have no idea where this relation comes from, why stellar age or stellar mass, because we're always on the RGB, so we're looking at higher and higher mass stars as you go down. Why this has any effect at all, we have no idea, and this is a totally unexpected result when we started our survey. So, coming back to 1978, this was a pretty amazing cluster. So this is the youngest cluster where we have found multiple populations to date. And this is an optical CMD. And so if you zoom in on the CMD, we can just select stars on the subgiant branch. The subgiant branch is particularly good at this age. Because this cluster is young, this is extremely sensitive to age. Okay? And so I told you in the past, previously, if you do this for ancient globular clusters, the kind of best constraint on age, you can say they're coeval within 300 million years. Because this cluster is only 2 gig years old instead of 12 gig years old, we can do significantly better. So we can put the tightest constraints to date on different ages. So how do you do it? So you first select your subgiant branch stars here. You then look at it in your favorite color, and you see that it no longer looks horizontal, it actually goes vertical in this particular CMD, and you can see it's bimodal. And you can compare that with models. You can actually see the different populations on the subgiant branch. So this is the normal population, this is the enriched population or second population, and then what you do is once you've selected your stars, you then go back to your optical CMD and overplot the two stars. And what you should see, what was expected, is that they should differ vertically, because that's going to tell you the age offset between the two populations. Okay? And we did tests on this, and we thought we could do better. The age resolution was going to be about 20 million years. So we got really excited because, just to remind you, for the AGB scenario to work, it has to be 30 million years or more. And so this is kind of one of the fundamental constraints you can put. Are there real age differences within clusters? And the result, as you go through this, is that we got the age difference was 1 megayear plus or minus 20. And this is the kind of a fundamental constraint on this. So essentially, to all practical purposes, the populations within these clusters are coeval. Now, in principle, this agrees with any high mass star scenario, but yeah, it was pretty surprising just how well we can do. And just yesterday, we got the new data of a cluster about the same age, a little bit older, about 2.5 gig years, and it looks like we're going to get the same basic answer. We see the chemical spreads. We can do this whole thing, and so this seems to be just a common phenomenon within these massive clusters. So, takeaway messages from this. Globular clusters host multiple populations within them. This is seen in the chemistry, and the chemistry is what's reflected in their strange CMDs. So the strange CMDs are picking up either helium spreads or CNO spreads, and that's how we can see that they're not simple stellar populations. I didn't have time to really talk about this, but they don't seem to be limited to globular clusters. We actually see relatively high fraction of these stars in the bulge of the Milky Way. Now, whether or not they come from disrupted clusters is another question. And we see evidence possibly in the central regions of early type galaxies, where they show the same type of signatures, increased nitrogen, increased sodium, decreased oxygen towards their centers. We can say that globular clusters are still forming today. At least we see young massive clusters forming that have all the properties that we'd be expected to see if we could look at high redshift. And in fact, just recently with the lens HST fields, we can start peering into redshifts of 4 and above. We can actually see these things on 10, 20 parsec scales. And again, we don't see anything really unique and these are true clusters forming at high redshift. They look just like young massive clusters today. We don't see evidence for age spreads or multiple bursts in young clusters, either through resolved photometry or integrated spectroscopy. Observations of young massive clusters appear to rule out the popular scenarios that have been put forward, including my own. I'll end with that in a little bit. The HST survey I presented, we hoped was going to kind of solve the problem. We were either going to find it everywhere, or we were only going to find it in the ancient clusters, so we had really pinpoint what it is. And instead, we find this step function, where clusters above 2 gigayears seem to show multiple populations, clusters below that don't. And we also see a strong function of age. So older clusters show larger spreads than younger clusters, and also with mass. Higher mass clusters show larger spreads than lower mass clusters. And these are all unexplained phenomenon that don't also work in any of the scenarios that have been put forward. And we don't see any age difference between the first or second populations. So that's kind of it. We have no idea what's causing this. And so new ideas are needed. We experimented a bit with different ISM physics, following in Phil Hopkins' models of possibly separating dust from gas in extremely massive turbulent cores that might form these massive clusters. That doesn't seem to work, or at least doesn't explain the observations. Is this something to do with stellar evolution? Kind of when you see a dependence on age, you kind of the first thing that pops in mind, but there's nothing that we can think of that would come into this. And so just to drive home the kind of state of the art, I'd like to show this diagram here. So these are the 4 main scenarios that have been put forward. So the AGB one that I described in some detail, fast rotating massive stars, which is the same thing, but then using rapidly rotating stars. These are these 10,000 solar mass stars out there that you can kind of form through the merging of stars in very early kind of proto-cluster phases, the first few million years. And then this was the scenario that I came up with Selma and others, so early disk accretion that doesn't invoke multiple generations of stars, but basically stars could accrete essentially from either these stars or those stars. And as I said, these were developed after the young massive cluster constraints came out, so they satisfy those by definition. But you can see is that, you know, if you actually look at the detailed abundances, the cluster-to-cluster variety or stochasticity, the mass budget problem, all these types of scenarios, these models really fail as soon as you start looking at anything quantitative. But this is just the tip of the iceberg. In fact, we could go on for hours here. That you choose your favorite constraint, and if you actually apply it uniformly for each of the scenarios, you see that they're just not doing well at all. And so while these models are conceptually straightforward, and there's no reason to think that clusters couldn't undergo multiple generations of star formation. You see it in dwarf galaxies. It just turns out that clusters don't. And so therefore, we really need new ideas. And hopefully I've motivated someone here today to start thinking about this, because my guess is the solution is not going to come from a globular cluster person. It's going to come from somebody from a totally different perspective or field. And I'll end there. Thank you.
Are you really motivated to say that one model is going to fit all? I mean, it would seem that we may have to have 4 models or 5 models. Mm-hmm. That one's not going to, fit all.
Just to say that we experimented with that as well. We talked about it a little bit. I should point out, sorry, if you want to read an excellent review on the subject, that we experimented a little bit. You say, okay, well, it doesn't have to be one of these models. Let's say, and let's combine those two. We use the best of each one. It still doesn't work. And the one that really drives this home, you can see just what an uphill battle this is going to be. Is you look at the abundances. Okay, so you can say abundances. Well, that depends on the yields and how much do you believe the yields of stellar models. Let's say you don't believe them at all, because you're really pessimistic. Okay, fine. Then I'll take one globular cluster, pick your favorite globular cluster, and just see blah, blah, blah. And you take the yields from that cluster, and you say, okay, could those yields, in the most optimistic case of whatever knobs you want to turn, dilution, whatever, explain any other cluster? And that's just no.
Okay.
So the yields, so there's nothing like, oh, we know it's HB stars, so therefore let's come up with some crazy way to make HB stars work. It's just on a fundamental level. These models are failing. The uniqueness of clusters, the actual observed abundance variations and how they interact, they just really seem to be out of range of any of the classical ideas we put forward. So, yes, I don't have the answer, so I don't know which way to go.
Okay. Yes, question?
I'm just curious if you've been able to do anything with kinematics. Like, are you able to see any difference between the populations kinematically, or do clusters that have multiple stellar populations have different kinematic signatures than those that don't? Or?
Yeah, that's a great question. So within a cluster, this is kind of the next phase that people are really going into. So you go on, you get dynamics through Gaia or through radial velocity of hundreds or thousands of stars within clusters, and you can see, well, are they different? And the answer is simply yes. But that wasn't too surprising, because you know that the second population, the enriched population, are more centrally concentrated. So therefore, just by following the potential, they're going to have different, right? And then you could say, well, people have looked and done simplified models to say, okay, what on top, if you ignore that difference, is there a difference, say, in rotation? And there's some models that say, yeah, the second population should be rotating because you should have angular momentum left over from the aging winds or something like this. And so people went out and looked for it. And the first cluster they say, oh, this agrees with the AGB scenario. And the second cluster they looked at said, we get the exact opposite. And so it's a totally open question right now. And I think that, the data is now there with Muse in the centers of these globular clusters, and in the outskirts, they have hundreds of stars now in a handful of clusters, that we're going to be able to really pin that down. And so maybe that's where the answer is going to come in. But right now, we don't get a solid answer other than the obvious, what was expected.
Yes, you go. Yes.
When you show this plot with the multiple population, where there were crosses and check marks, you mix the populations of LMC and SMC clusters.
Yes.
And there is very tight age metallicity relation. Well, there are tight metallicity relations for both LMC and SMC, and they're different. Have you tried to look into the to replot this diagram, but instead of plotting age, to plot the metallicity on the other axis?
Yes. That's
what do you see?
Nothing. So just to say is that, so these guys are all SMC,
Oh yeah.
and they're all low metallicities.
Yeah, there are no clusters in the LMC in this age range.
So that's minus 1.5 or to minus 1. That's LMC, and that's at half solar. So it's not different. And then if I go a little bit, these 4 are mixed bag, 2 are LMC, 2 are SMC. The 2 in the SMC are the same metallicity, 2 in the LMC are the same metallicity. So no, there doesn't seem to be any trend with metallicity within them or environments. And so it's hard to really think also of something environmental that would kick in 2 gig years ago. But for both galaxies, LMC and SMC. And just to say, I didn't talk about this, but I mentioned a little bit that we have integrated light of a really massive cluster at 3 gig years. We also have integrated light constraint of a 500 or 600 megayear cluster. This tend to be 8 solar mass cluster, and we don't see evidence for multiple populations there. So this age effect, this age trend seems real, and it seems to be independent of the environment.
Can you show us the Rosetta Stone cluster and how it splits? You had a
Yeah,
fancy color.
that's right. Yeah, that's just the subgiant branch, just to be clear.
Yeah. So
Sorry. It's a problem with built-in slides. Yeah.
So on the left, it looks like a mess to many of us.
Yeah.
And then on the right, in the gray histogram, it looks very convincing. But what is the chance that this, since this is your Rosetta cluster, right? So let me pick at it. What is the chance that you get this by luck? How many clusters would we pick that don't have a split where you might see one? You might not see one.
Yeah. That's a good question. That's fair. I don't know. I don't know what the chances are. I don't think we did it. So just to say, I can say we did the fancy Bayesian analysis where we don't say stars using their population as a probability. So we did the full on that, and that's where the answer comes from. But just say, now we have a second cluster where we see the same thing. But yeah, and so the other thing to say for this cluster, we also now, for those aficionados, we also got these very UV filters for this cluster now, which allows you to split things even better. This F275, which is what the Maloney and Kyoto use, that really nicely splits. So hopefully the data will just get better and better, and then you can really convince people. But if it was just by chance this happened, yeah, maybe. But then we have at least one more cluster coming where we're going to be able to put the same type of constraints. In fact, maybe 2 more, now that I think about it. We might get lucky with the second one. So then we have 3, and so it's a sample of 3. So the answer is right then.
I think it would be good to bring the field to the level where there is confidence levels in the test all these things.
Well, that's asking too much.
In the Milky Way globulars, if you had really exquisite astroseismic information, would that be a new way to get at some of these issues? We get really precise masses.
Yes.
Or this interior.
Yeah, I think that could be really cool. And in particular, helium. Helium should have a drastic effect on this. And so, when we say there's helium spreads, that comes out of models, but you can't calibrate those models. No one's ever observed a helium star in a binary where you can get a direct mass estimate. And so, there are extrapolations for what's known there. And so, yeah, I think that could be really cool. And so there's one cluster that's in the Kepler footprint, K2 footprint, which is N4. And unfortunately, that cluster is also one where it's got very small multiple populations. So it's got very small helium spread. And so it's probably, so people are looking at it, maybe we're going to find something cool, but I'm a little bit skeptical. That's like the one cluster you wouldn't want to go to, but it just by chance happens to be in the field of view. But for future missions, yeah, I think that's going to be a way forward.
And you made another point. I mean, all of this is dependent on your models and your stellar evolution models. I mean, we have measured helium maybe in 2 clusters directly, but otherwise everything, even your small age spread, is very model dependent. So
Yeah, I think that's right.
maybe we should be looking somewhere else, not.
Yeah, that's right. So I should have made a stronger, because it's becoming clear. This exact point is exactly right? So which constraints are model dependent?
Yeah.
Now, they're pretty solid models. It's not like, you have to say all the ice cones are wrong.
They differ. They do differ.
That's right. But
Yeah.
so this result, we use different isochrones, of course, and you get the same answer. The absolute age changes all over the place. 2 gig years, 2.5, 1.8.
Yeah.
That's there. But the age difference was the same in all the models done. But all the different, the direct constraints of lack of star formation in clusters, or the lack of gas, that's not model dependent.
Yeah.
That is just a direct
It's not
observation.
there. Yeah.
So it is a mixed bag. I think that's a good point. You're right.
Yeah. Charles?
So, looking at this diagram, if I understand you correctly, those 100 or so stars are all the same mass. They all formed at the same time. For the first 2 gigayears of their life, they all looked the same. And then somehow at 2 gigayears, they separated themselves. Is that?
Well, that's the conclusion that I'm forced to. other way to look at it, what I was banking on until last week, was that no, it is the fact that these clusters these stars all have masses just below 1.5 solar masses. Therefore, they were not rotating. They were all magnetically braked. And I know that from, we can go into a whole other talk on why I know that. And this cluster, you don't have to send them into turn off. These things were there. Therefore, it was a mass dependence. That's what I thought, for some reason, and I don't know why, but that below 1.5 solar masses, this chemical anomalies could manifest. And above this, it couldn't. Because we're always looking at evolved stars, so we're seeing this age dependence. So what do? You go out and you get deep HST observations to look for multiple populations on this type of main sequence. And this is what Yvonne has been doing. I don't know if you plan to give a talk, so I don't know if I can give the game away. But the answer is, yeah, we don't find it on the main sequence. And so therefore we're back in the most extreme case of the scenario, the absurd scenario you just put forward.
Binaries?
Yeah, we experimented with binaries and can't make that work either. We tried this, but why this? So I'm still hoping that maybe there's something wrong with the data, that why we couldn't, because it's just too crazy now, right? But that's the situation as of this morning.
I'll assume that you and Yvonne can work that out. But I wanted to ask about the mass dependence, the cluster mass dependence.
Yeah, okay.
In some ways, I find that more surprising.
Yeah, right.
This whole thing, this dichotomy of 2 gigayears turns on at some mass scale of order, or whatever it was, 3 by 10 to the 4 or something.
Yeah, something like this.
Can you just say more about like what are the environmental differences that stars find themselves in clusters of 10 to the 5 and above solar masses versus 10 to the 4 and below solar masses? Because something in that apparently triggers this behavior.
I agree. And so one of the things, so if you go now with this HST survey of Kyoto and collaborators, they went up to 10 to the 6 solar masses. What they find is 90% of the stars are anomalous and 10% are normal. And then 10 to 5 solar masses, it's only 6% are strange and 40% are normal. So it's a very clear mass dependence, and it's consistent all the way down. And yeah, you could continue that trend and go all the way down to 10 to 4, and what you'd find there is 80% of it should be normal and 20% are anomalies. So maybe they're just hard to tell. But where this dependence comes from is also a mystery. Because if you believe in the AGB model, or fast radiating massive star model, you get the same amount of enriched material per unit mass. It all scales. And these are high mass clusters, so their IMFs are all fully sampled. Except for maybe these 10,000 solar mass stars. Okay, so let's ignore that. And so there shouldn't be any dependence on mass. But there's a very strong one. And so where this comes from and what could come in, I don't know. There is one thing that I mentioned yesterday that works on a totally different topic, but similar massive clusters. There's one thing that does change between stars that are in the field versus in a massive cluster, and that stars in the clusters, massive clusters, rotate faster. You have a larger fraction of your stars near critical rotation than you do in the field. Great, that's got to be the answer, right? Well, except for this only happens in old clusters, and these stars don't rotate. You can go and measure that. They all have very low rotation rates. So maybe they were born with fast rotation rates and were slowed down that somehow led to this chemical anomaly. But yeah, I don't know. But so what's the only difference? That's the only thing.
You say the word field, but that's, I guess I really want to know about 10 to the 4 solar mass clusters.
Right.
So is it really the case that, it's not just any old 10 to the 4 solar mass cluster, it's a 10 to the 4 solar mass cluster that can survive for multiple gigayears.
Right.
So it's, what is different about those clusters? And is the stellar density higher in the high mass cluster?
It is, because they more or less a constant radius, but it's not like a step function.
You don't need a step function.
Like a core collapse or
What's that?
the core collapse in a cluster?
So most of these clusters have not undergone core collapse. So those are the kind of higher density, older ones, the higher density. So that's not there. When a star forms, if you go back to when a star, stars have disks in high density environments, you might disrupt the disks. So, and that's what my personal belief is why stars are more rapidly rotating in clusters, is that you somehow destroy the disk. Does that have an effect somehow? Why? But then, why does that matter? I don't know. But that's one difference. Yeah.
Josh was next, and then
So at the beginning, you mentioned LMXB populations,
Yeah.
which is something that I've worked a lot on. But
Okay.
the question I have is the preponderance of LMXBs in globulars is not uniformly distributed amongst all globulars, as I'm sure you know. Clusters like Terzen 5, Terzen 2, these bulge clusters that are relatively metal rich. So my question is, how much could mass function, stellar mass functions, be involved in explaining some of the questions that you've been pursuing?
Are you meaning, so variations in the stellar mass function?
Variations in
clusters?
stellar mass function. Because what we see, of course, in these LMXB clusters are a preponderance of neutron stars, no convincing direct evidence for black holes.
Right. Until
Neutron stars.
recently.
Well, there is one that's
Yeah.
an interesting case.
Yeah.
But they're certainly not there at the rate that one might have expected,
Yeah.
given the neutron star populations that are there.
Mhm.
But back to the either metallicity or mass function or both, I'm just wondering how much those might be involved with multiple populations.
Yeah, I mean, it could be, right? Nothing's off the table now. We have to
Sure.
figure it out. So just say for young massive clusters, we do have constraints on the IMF within them. We can see young clusters, they have
Sure.
massive stars, so you
Yeah.
know that they're there. You can get dynamical masses, so you say that they're not too different from, but there could be, systematic variations, absolutely, but kind of the factor of 2 level. But just to say, also on that, recently with Hubble, behind lens clusters, they've been observed these protoglobular clusters at redshift 4, 5, and 6. And they also seem to have massive stars within them. So, why some clusters are able to hold on to their black holes and neutron stars while others don't. There could be some dynamics there. Denser clusters might get rid of them more easily. I'm not entirely sure on how that exactly goes. There's some hope, in fact, with Gaia, with dynamics. You can actually work out the population of black holes that exist dynamically to try to put constraints on that. So, to me, there's definitely evidence pushing that the IMF is not varying crazily within clusters, in the sense that it's not that some clusters have no high mass stars. I don't think there's much evidence for that. But their further evolution, you see the mass function changing, at least you get rid of the high mass stars evolve, the low mass stars get ejected. So, depending on its tidal history, it changes. But I don't know, how that can explain this. But it's worth it. Think about it.
Mark, you had a question.
Yeah, so what happens if you form clusters, lower mass clusters, in
Yeah.
slightly different areas in the galaxy under slightly different conditions and then merge them?
Yeah, thank you for bringing that up. I should always mention this because it always comes up. That would work, maybe, if, there you go. If we found some things that were only up here and some things that were only down there, then you merge them and then you'd get big. And then they would also have to be very near each other because we have no iron spreads, but that's fine. But the fact is we never find just those. There's always this spread. So you'd have to then invoke that you always happen to get rid of. And even in the young clusters where you actually resolve stars, you never see stars forming up there. And so, that was one of the original ideas, was you form a cluster, then it all of its winds and ionizing sources ionizes a nearby cloud, which then triggers star formation, whatever, and then they merge. And that's fine, it probably happens sometimes, but you wouldn't end up with these kind of chemical spreads, just because you don't end up forming stars normally that only have one or the other.
Question in the back? Yeah.
Yeah, so if I understood the plot correctly, this 2 gig-year break is only based on globular clusters in the LMC
And SMC.
and SMC. So 2 questions. One, is there something that happened in the LMC and SMC 2 gig-years ago that might have triggered this? And 2, could you look for globular clusters younger than 2 gig-years, not in LMC and SMC, to see if they exhibit multiple populations?
Yeah, it's a very good point. So to answer the first question, it is, I'm sure you could find something that happened at 2 gig years, in the sense that there's been so many star formation histories published of the galaxy. I'm sure you could find one of them that was published with a burst at 2 gig years, or 3 gig years, or whatever you wanted it there. But it's hard to think of a galactic scale phenomenon that would then filter down onto the parsec scale of this. But in simple terms at least, the star formation history of the small and the large magnetic clouds has been constant for the past 2 to 3 gig years, within a factor of 2 or 3. So there's no giant burst or anything that's happening there. But so then can we do this elsewhere? And that's where it gets dicey. And the answer is simply no, at least not using these techniques, because we don't have, already by M31 and M33, you can't resolve the clusters enough with the proper photometry to do this kind of thing. So we're now trying to do this integrated light, which brings a lot of caveats with it as well. And there, for the 2 clusters that we've done that have straddled this border, both extremely high mass, so that mass shouldn't be playing a role, is that we find it there as well. The 3 gig a year shows clear evidence for being very enriched in sodium, and the 500 meg a year one does not. And and it's even more massive, so it should even have an even stronger one. So, I don't think, honestly, even though I'm the first author, I don't find it overly convincing, just because I'd love to be able to resolve the stars and do this kind of stuff. But unfortunately, we just don't have the samples where we're going to be able to, and I don't see that happening anytime soon.
Okay, we had 2 more. Aaron and then Ellen.
Okay. I just wanted to throw out a provocative statement, which I nevertheless believe to be true. If you look at detached eclipsing binaries in old globulars, which are distinct from massive interacting binaries in the sense that they are both low mass and not interacting. And they have survived until today to be observed by us. And there are a dozen or 2 dozen of these that are known in several clusters. None of them appear to belong to the second population or second generation. They all appear to be first population or generation.
Yeah. All right, so thanks for bringing that up, because we have a really cool result we're going to submit next week. We have MUSE observations. So MUSE is an IFU on the PLT, and it's magic. So you get spectra of thousands of stars per cluster within it, and got 25 epochs. And so you get spectra of radial velocity variables, right? And it's the center of the cluster. And so this had been done previously and said, okay, and they've been found. So most, the binary fractions, the 2 populations are different by a factor of 3 or so. And this was said, okay, well maybe then, because your second population form is more concentrated, that over time it evolves, and that's why. So you form the second population stars more dense, so you break up the binaries. But we're only sensitive to very tight binaries. They're not affected by this. But we find the same factor of 3, which means the star formation process knows which population the stars are formed. It's a primordial effect. And so binaries, normal star, are only found really in the normal population, and binaries are not commonly found in the second population. That's one more piece of the puzzle.
Salma, do you want to? That's the last one.
You touched a bit on this, but there is several people in the community that believe this also to be the sites for black holes to find a companion, and then eventually merge with those. And so these ideas, they need several populations of 20 or 30 solar mass black holes to sit in some of these. I want to invite you, if you have anything to say, maybe with respect to the formation scenario or the constraints that you have today.
So, I don't have much to say. I mean, the main constraints on black holes and clusters actually put forward Jay Strader, who was here for a number of years. We used radio and found that there's very few black holes, or all in the upper limits. No, he actually found some pretty black holes. And then Sebastian Kamen and collaborators found one stellar mass black hole in NGC 3201, and just to give the game away, they found a second one in the same cluster that's been published soon as well. But these are not 30 solar mass black holes. These are the six
solar mass.
Thank you. I remember. And so, I don't know. But the one thing I can say is that the community was very excited about intermediate mass black holes in globular clusters for a number of years. And with all the evidence coming through now, it's pretty clear that they don't exist for the majority of clusters.
They're all gone as of now.
What's that?
They're all gone as of now, because some cluster, they appear then disappear. One paper rediscovered them, then another one. It goes like, right now the score is 0. A few months ago it was 1. But
no, I actually agree. So that would have gone in that direction, and I wanted them to be there, but I agree. Actually, I think it's pretty clear now that they're not common if they exist at all. Which brings up another question, is of Megasen and others were the centers of dwarf galaxies. And most dwarf galaxies host intermediate mass or supermassive black holes in the center. Why don't we see them in a Megasen or M54 today, which we know are the nuclei of these galaxies, and they don't show it? So that's another little fun thing to throw out, like a mystery of globular clusters.
You've given us lots to think about. Thanks for a great colloquy.
Thank you.
Normally, so that's a delta.